All right, so the next problem we're going to do is another exponential growth or decay problem. And what I had on my screen was a typo, and so I wrote in, and hopefully this is what you have too. If it doesn't, we're going to do this one. But the first thing to notice again is what kind of graph this was going to create. My b value is 1/5, so this is going to be decay. So in our brain, we need to think that it's going to look something like that. Okay, and so from that, we start with, we can start making our table, and we're going to have, if I plug in 0, and if I just think that this is like f of x equals 1/5 of x. So that's like my parent function. Anything to the 0 is going to be 1. And then if I plug in 1, it's going to be 1/5. And if I plug in -1, it should be 5. Because when you raise it, remember, to the negative, it makes it turn into the reciprocal, which in this case would be 5. Okay, so if I graph those just for my parent, so I have an idea of what it's going to look like, and then I can apply the transformations to it, it'd be 0, 1, 1, 1/5, and -1, 5. And so our parent is going to look something like this. Okay, so that's the original. But then we need to go label all of our transformations and apply them to the graph to make sure that we graph it correctly. So since this is in the exponent, this is going to be right 4, and that applies to the x value. This plus 3 is going to be up 3. And then this 2 out in front is going to be a vertical. And then since it's bigger than 1, it's going to be a vertical stretch of 2. Okay, and then we need to go apply those. So the right 4 affects the x value, and it's the only one that does. So this is going to be just adding 4 to each of these. So that's going to turn into a 4. That's going to be a 5. And this would be a 3. Okay. And then when you're doing the y values, you have to go in PEMDAS order. So since they're both affecting, the vertical stretch and the up are both affecting, we need to do PEMDAS first. So we're going to multiply by the 2 and then add 3 to our y values. So each of our y values are going to get doubled first. So that's going to be a 2. And that goes to 2/5, and this would be 10. And then I need to add 3 to each of those. So then finally we'd be at 5. And then 2/5 plus 3 is like 2/5 plus, what would that be? 15 over 5. So that's 17/5. That's 17/5, and then this would be 13. So when we go to graph, we're going to get 4, 5. 4, 5. That would be our new turning point. So again, let's put turning. It'll be at 4, 5. Okay. Our horizontal asymptote, the whole graph got pushed up 3. So now our horizontal asymptote is at y equals 3. And so we need to go, put our horizontal asymptote, y equals 3. And then we need to go graph our other values. So at 5, we're going to be at 17/5, which is just past 3. Just a little more than 3. So we go to 5, we're going to be just over 3, so it's going to be like right there. And that's going to be the right-hand portion. Since it's decay, it's going to be where it's flattening out. And then if I plug in 3, we're supposed to get 13. So if I go over 3, we're going to be way up here. And so our graph is decaying very fast, and it gets to this turning point, and then starts to flatten out. And it should be about like that. Okay? The domain would be -infinity to infinity, and then the range, again, isn't going to pass this horizontal asymptote, so it's going to be 3, infinity, because we're staying above it. All right? So there's number 5 and number 6. Again, just be mindful of growth versus decay, going and labeling all of your different transformations, and filling out the key information that it asks you to right here, and it should be pretty good. Okay, so modeling growth and decay, we can use some different equations to represent kind of what's happening without necessarily going through the whole graphing process. So if we're growing or decaying by a constant number, we can use either one of these equations. Okay, the growth one is, growth and decay equations are almost the same, except growth, you're going to be adding the rate that you're growing at, but for decay, you would be subtracting the rate that you're decaying at. Okay, and so it'll kind of make sense once we do an example, but let's look at number 9. So number 9 says the first U.S. census was conducted in 1970. At the time, the population was just almost 4 million people. Over the next 200 years, the U.S. population grew approximately 2% each year. 2%. So we need to write an equation modeling the population from t years after 1790. Okay, so if we're writing an equation for population and it's based off of time, that's going to be, instead of f of x, it's going to be population of t being time. And so the values in your equation, since we're doing, the population is growing, we're doing growth, this lowercase a is always your initial number you're starting with. So our initial number we started with was 3,929,214 people. And then it's going to be, that's like your vertical stretch number out in front. And then you need to do 1 plus the percentage that we're increasing. So this would be 1 plus, but when you go and put it into the equation, you do not write it as a percentage. We need to write that as a decimal. So the 2.03% annually would turn into 0.0203 for our rate to the t, to the power of t, because t is the number of years. So if we were going to actually calculate, well, I guess we need to simplify this equation first. We do 3929214. This simplifies to 1.0203 raised to the t power. Putting that as in its simplest form makes this value a really specific value. When we were talking about it a minute ago, we talked about if the value of your base is bigger than 1, then it's a growth equation. If the value is less than 1, then it's a decay equation. Well, we're dealing with a population growing after all these years. And so us having a b value right here that's bigger than 1 is really, really important. Really, really important. And I just realized I don't know why I put a 4 right there. There should be a t. Okay, but that would be the correct simplified equation for part A. It says write an equation modeling. That's the equation modeling. Okay, use that equation to predict the population today. And so we are currently in 2025. So if we did 2025 minus 1790 and subtracted that, let's see, this would be 1, that's going to be a 9, that's going to be 11, and well, I don't know why I did that. Yikes, it's been a while. 5 minus 0 is 5. Then I need to borrow, so that's going to be a 1, that's going to turn into a 9, that's a 12, so that's going to be a 3, 2, so it's been 235 years. Okay, it's been 235 years since 1790. Okay, so the t we're going to use, so p of, and we're going to plug in 235 because that's the number of years since. And then we're going to use that equation, 3929214 times 1.0203 raised to the 235th power. Okay, understandably, no way we're doing that with without a calculator. Okay, so let me pull up my calculator so we can get an accurate number. Let's get as close as we can on this number. All right, so when you type it in, 392, 9214, parentheses, 1.0203, close parentheses. Click this little caret on the middle right for your exponent, 235. Okay, so we're raising that to the 235th power, and we get 4.419 blah, 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 and then that e to the 8th. That E8 is really important. Okay, that's scientific notation in our calculator, and it's telling you that you need to move the decimal 8 places to the right. So the number is going to be 44193565969. And so if the decimal is starting right here, then I need to move it 1, 2, starting right here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to have it right here in between the 6 and the 9 in the very back. It's going to go right there. And so this would be, looks like 4 billion, about 4.4 billion people. Okay. Unless I counted that wrong. Did I count that wrong? 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. 419, 3, 5, 6, 5, 9, 6, 9. And it says e to the 8th, so we counted. Or did I count 9 or 8? Yikes. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I put in the wrong. Oh, man. Never a dull moment out here, especially when you're recording a video. All right, let's see. Okay. Let's try to make this as accurate as we possibly can, because that doesn't really make sense. How would I get 4.4 billion people in only the U.S.? So let's make that a lesson right there. If you get a number that doesn't really make sense, there's probably a reason it doesn't make sense. Okay, we're moving into 8 spots. Let's do it. 1, 2, 3, 4, 5, 6, 7, 8. 8 right there, which would make this 441 million. Almost 442. Let's put 442 million. And that makes way more sense than the billion that I got the first time. All right, so 442 million people, which, if we went and looked it up, that's probably not crazy off. I want to say that we're a little under 400 million right now, but just an approximation, okay? So we're going to repeat that and do the same kind of idea, and let's go on to number 10. So it says a cup of tea contains 35 milligrams of caffeine. The average teen can eliminate approximately 12.5% of caffeine from their system per hour. Interesting. So we need to draw a graph to represent the amount of caffeine remaining T hours after drinking a cup of green tea, and then we're going to estimate how much is in the body, a teenager's body after 3 hours. Okay. Some of y'all that I've noticed, y'all come into class almost every day with like a Monster or an energy drink of some sort. So this is kind of applicable to some of y'all, except that there's way more grams of caffeine in those energy drinks than this cup of green tea. Okay, so let's do it with this. So we have 35 milligrams of caffeine, and it says the average teen can eliminate. That's an important word, eliminate. So is this going to be exponential growth or exponential decay? Well, eliminate would be that it's going down. We're having less of it, so this is going to be a decay problem, which means we're going to use the same equation, except instead of adding our rate, we're going to subtract our rate. So our equation is going to be A of T, the amount of T, oh, that was a pun, after T hours equals 35, because that's our starting point, right? We're starting with 35 milligrams, and then we're going to do 1 minus, and then always put this percentage as a decimal, so 1 minus 0.125 raised to the T hours. So that turns into 35 times 0.875 to the t. And then again, this number makes sense because we're getting rid of caffeine. And so this b value, base value, is less than 1 and greater than 0. So that would be the exponential decay that we needed. And so if we tried to graph this, and we would probably need to use a calculator to be able to graph it, but I'm just going to give you the values. If we plug in 0, anything to the 0 is 1. 1 times 35 is 35. If I plug in 1, you would get 30.6. If we plugged in 2, we get 26.8. If we plugged in 3, we would get 23.4. And obviously we could keep going. And so we get that the graph we could draw would be, this is like in the 30s, so let's go, we'll do 10, 20, 30, 40, and that would be, we need to put hours on the bottom, 1, 2, 3, 4, 1, 2, 3, 4, and so our graph is going to look something, oh wait, no. It's going to look something like 26, 33. It's going to look something like that, where it's decreasing, but it turns out it's decreasing kind of slowly. Okay, so it says estimate the amount of caffeine in the teenager's body after 3 hours of drinking a cup of green tea. And so we would do A of t equals 35 times 0.875, and then we're doing 3 hours, so we're going to raise it to the third power, and that gets us a grand total of 23.4, and that would be milligrams. 23.4 milligrams of caffeine would have been eliminated. Okay? So, exponential growth, exponential decay, there's some really important ways that we can utilize this, but that is it for today's lesson.